Hi dear students, welcome back to the class. So far we were discussing about sets, right? We defined a set and we used different notations for set, and we said that we can represent a set in two different forms, namely set builder form as well as roster form, isn't it? And then we have done several problems using those concepts, and then we defined equal set, null set, etc. In this class we are going to define, or we are going to discuss with some interesting facts about set. Suppose that, let me consider two sets at the beginning. Suppose that capital X be the set of all students in the school. Students in the school Giridipam. So capital X is nothing but the set of all students in the school Giridipam, which means that X contains the set of all students who studies in Giridipam in the current academic year. Let me be specific about that set. Let it be in the current academic year, and let Y be the set of all students studying in class 11A in 2020. Let it be in 2020. So capital Y is nothing but the set of all students studying in class 11A in 2020, whereas capital X is nothing but set of all students in the school Giridipam in 2020, which both are sets which are well defined because it is the same for all and everyone, right? Let it be there. And now we are going to say an important as well as interesting fact about set. See, you can observe that all students studying in class 11A in 2020 or 2020 is also the student of the school Giridipam, isn't it? So in this set, all the elements in this set comes to be an element in the set X also, isn't it? So we can say that every element or every student in the set Y is also a member of every student in the set X, which means that all students studying in class 11A of Giridipam will fall into the category of set of all students in the school Giridipam, isn't it? Let it be there. On the contrary, see, all students studying in the school Giridipam. So here we can have students in class 11A, students in class 11B, students in class special batch, and students in 12A, 12B, etc. So all the elements in this set need not be in this set, right? A student in class 12A does not fall in the set Y, isn't it? So we can notate these two facts in a special way using set. We know that, first of all, we said that all elements of Y or all members of the set Y is also in the set X. Then we say such sets as subset. See, what is the name? Subsets. Subsets, which means that whenever an element belongs to the set Y, the same element must be in the set X also, which means that when all the elements in the set Y is also in the set X, then we call it as Y is a subset of X, and we name it as subset. So we read it as Y is a subset of X, which means that every element of Y is also in the set X, whereas you can easily observe that all the elements of the set X need not be in the set Y. Then we can say that X is not a subset of Y, isn't it? Then we denote it as X is not a subset of Y, and read as X is not a subset of the set Y. So now you remember that the only thing or the only condition for a set to be a subset of another set is that all the elements or all the members in the set must be in the other set also. Here you can see that all the elements in the set Y is also in the set X. Then we can say that y is a subset of x, isn't it? Now you can easily observe that a set itself is a subset of that set. See, A is any set, let it be, it can be any set, then definitely it must be a subset of itself. Why? Because every member of A is also in the same set A. It is verbally some more little bit difficult to or confusing, but think that every element of the set A is in the set A, then we can say that A is a subset of itself, and we denote it as a subset of A. A can be any set. This is true for all and every set around us. So a set is a subset of itself. This is a very important point. Note that a set is a subset of itself. Now we know that the null set, we used to denote the null set by phi, which means that a set which does not contain any members in it. Clearly, phi will be a subset of every other set for any set A. Why? Because literally speaking, phi does not contain any member, isn't it? So we can say that every member of the set phi will be a member of any other set, because phi does not have any member. So we can easily say that phi is a subset of any other set. Always remember these two results. A set is a subset of itself as well as phi, the null set, is a subset of any other set. Okay, now let it be there. Now suppose that a set A is a subset of B, which means that every element of the set A is in the set B, isn't it? Now suppose that B is a subset of A also, which means that every element of B is also in A, isn't it? See, these two conditions, when these two conditions satisfies together, what we can say? Think about it. Every element of A is in B. This statement gives us that every element of A is in the set B also, and this statement tells us that every element of B is also in A, which means that every element belongs to A is also in B, as well as every element belongs to the set B is also in A, which means that these two sets will be equal sets. Remember the definition of equal set. Two sets are said to be equal only when each and every element belong to the one set must be in the other set, and vice versa. So these two conditions tells or gives us the same result. Each and every element belongs to A is also in B, and as well as each and every element in B is also in A. Hence we can say that whenever we are given with these two conditions, it implies A is equal to B, or A must be equal to B. Read this symbol as implies. So this symbol stands for implies if you have confusion in understanding this symbol. So the third point is nothing but A subset of B and B subset of A implies A must be equal to B. So remember these 3 points. These 3 points are very important in understanding subset. A set must be a subset of itself because every element of the set is in itself. And phi must be a subset of A, which means that literally speaking phi does not have any members, and any set A thus can be for any set A, phi will be a subset of that set. So because literally phi does not have any members, and we have the definition of a subset as y is said to be a subset of X if every element of Y is in X, right? Since phi does not have any element in it, literally speaking this definition holds for phi also. So we can say that phi will be a subset of A for any set. And the next definition or next point to remember is A subset of B and B subset of A implies A is equal to B. So remember these 3 points very well. And what we mean by a set to be a subset of another set, every element of the set Y must be in the set X. We can define or we can write the definition in mathematical term as when A element of Y, which must be implies A must be element of X, then we can say that Y is a subset of X. So remember the definition of the subset of X. A element of Y implies A element of X, then Y is a subset of X. Whenever an element is in Y, then and if that same element is in the set X, then we can easily say that Y is a subset of X. That is the definition of the set. So we defined the subset, isn't it? Let us recall the definition again. A set is said to be a subset of another set. Let a set Y is said to be a subset of the set X if and only if for every element of Y, if it is in X also, then we can say that Y is a subset of X. That is, we can mathematically write the definition as Y is a subset of X if a element of Y implies a element of X for every a element of Y. So this is the condition. For every a element of Y, if a element of Y implies a element of X, then Y is a subset of X. Read this symbol as for every. So the definition, we used the symbol this to denote for every. Don't forget this. Very important notation. We use this in several situations. So read the mathematical definition of a subset as, we can read it as Y subset of X if a element of Y, which means that whenever an element, whenever a member is in Y, it must be in X also. Then we say that Y is a subset of X. Note the definition, very important. So that's about it. Remember that whenever a set is said to be a subset of another set, and also remember these three important, very important properties. A set is a subset of itself. Phi is a subset of A for any set. Phi is a null set. And if A subset of B and B subset of A together holds, then A equal to B. So these are the very important points from the session subset. So now we shall discuss about some of examples from the topic subsets. The first example is Q subset of R. What is Q and R? Q is a set of all rationals, whereas R is a set of all real numbers. Of course, it is very observable that every rational number is also a real number. So every element belong to the set Q is also in the set R. So we can easily say that Q, the set of all rationals, is a subset of the set of all real numbers. Now coming on to the second example. A, the set of all divisors of 56, and B, set of all prime divisors of 56. We know that when we consider all the divisors of 56, it will also include those divisors of 56 which are prime numbers also. So the set of all divisors of 56 contains all the prime divisors of 56 also. That is, all elements or all numbers belong to this set is also in the set A. So in that case, we can say that B is a subset of A. So that is the second example. And coming on to the third example, let A is equal to 135, set 135, and B is equal to set of all x such that x is an odd natural number less than 6. See, we have A is nothing but 135 and B is in the set builder form, x such that, what is the property of x? X is an odd natural number less than 6, which are 135, isn't it? So we can say that every member in this set is also in this set, right? So since this set is actually, what is 135, isn't it? So see, every element of this set is also in this set. So we can say that B is subset of A. And also note that every element of A is also in B. So we can say that A subset of B. Hence, whenever A B is subset of A and A subset of B, we can easily say that A is equal to B. And it is really easily observable that A and B are the same, right? So let it be there. So this is the third example of the concept subset. Now coming on to the fourth one. Let A is equal to A, E, I, O, U, which is the set of all vowels in the English alphabets, and B is equal to A, B, C, D. We can easily observe that here we have B, but B is not here. Hence, set B is not a subset of the set A. Also, you can easily observe that here we have E, but E is not here. So we can say that A is not a subset of B also, because when we can say that A is a subset of B, whenever each and every element of A is in B, but here we have E, but here does not we have E, we don't have E, so we have not a subset of B. Similarly, B not a subset of A. So this is the some of the major example from the topic subset. We can generate lot and lot of subset from our day-to-day life, from our surroundings, etc. So give a try for it. Now there is another important thing to be noted. Whenever we have a single element in a set A, then we call that set as singleton set. This is very important notation. So singleton set means a set with only one element. Please remember this. This is very important in the further movement of the chapter. Singleton set means a set with only one element. Also note that whenever we can have A is a subset of B and A not equal to B, then we can say that A is a proper subset of B. A is a proper subset of B. What do you mean by proper subset? Whenever A is a subset of B and A not equal to B. Now there is another method way to tell the same thing. We know that A is a subset of B. Instead we can say that B is a superset of A, which also means the same thing. So in order to say this thing, A is a subset of B, it is also the same to say that B is a superset of A. So remember the two terms, subset and superset. What is superset? When in this example Q is a subset of R, we can also say tell the same example as R is a superset of Q. Similarly, B is a subset of A in the second example. We can say the same thing as A is a superset of B, and likewise. So remember these two terms, subset and superset. Here we have A is a subset of B and A not equal to B, then we can call as A as a proper subset of B. Very important point. And also note that in the same case, whenever A is a subset of B, we can call the same case as B is a superset of A. So now we shall do the ninth example of your NCERT textbook. The ninth question is, consider the set phi A is equal to 1, 3, B is equal to 1, 5, 9 and C is equal to 1, 3, 5, 7, 9. Set of all 1, 3, 5, 7, 9. Insert the simple subset or not subset of between each of the following pair of set. Very easy. So the first one is phi and B. We know that phi is a null set, and for every set phi will be the subset of that set, because phi is a null set. It does not contain any member, so easily we can use the term subset here. Now coming on to the second pair, A and B. Look at A. It contains 1, 3, whereas B contains 1, 5, 9. So 3 is not in B. So we can say that A is not a subset of B, isn't it? Now coming on to the third pair, A and C. Look, A 1, 3 and C 1, 3, 5, 7, 9. Now all the elements in A which are 1 and 3 is in C also, set C also. So we can say that, or we can use a simple subset here. Now coming on to the fourth set, B and C. Look at B and C. 1, 5, 9 is in B, and the same 1 is in C, 5 is in C and 9 is in C, which means that all the elements of B is also in C. So we can use the symbol subset here. So we have phi is a subset of B. In the second question it is not a subset, but whereas in the third and fourth question A and B are respectively the subset of C. Now we shall solve example 10 and example 11. In example 10, it is asked that A is equal to A, E, I, O, U and B is equal to set of all A, B, C, D. Both are in roster form. Is A is a subset of B and is B is a subset of A? See, the first part is A is a subset of B. Here we have A, E, I, O, U. In this set, E belongs to A, isn't it? We have E belongs to A, but E does not belongs to B, isn't it? That means every element of A is not in B, so we can easily say that A is not a subset of B. Okay. Now the second part, is B is a subset of A. We can observe that D or B is an element of the set B, but here we don't have any B, so B does not belongs to capital A, which means that every element of B is not in A, so we can say that the set B is not a subset of the set A. That's it, the example number 10. Now coming on to example number 11. If AB, this is a very important example, please note it down. Let ABC are 3 set. If A element of B and B subset of C. See, A element of B, which means that the set A itself is a member of the set B. And B subset of C. Is it true that A subset of B? If not, give an example. Let us give a counter example for this statement. Suppose that, this is a very important question, understand this question very well. The first condition is A is an element on the set B, which means that the set A itself is a member of the set B. And the second statement is B is a subset of C, which means that every element of B is in C. So we can do that. Let A is equal to singleton 1, which means that the set contains only one member, which is 1. And B is equal to, see, A must be an element in B. So B is equal to set of all singleton 1, 2, 3. So what I have done is, see, B is nothing but singleton 1, 2, 3. See here, A, we know that A is singleton 1. So here A is an element in the set B. See, A is nothing but this set, singleton 1. See, singleton 1 itself is a member of the set B. Therefore, we can say that A is an element of B. And I construct the third set C as set 1, 2, 3, 4. See, every element of B is in the set C because singleton 1 is there in B. Singleton 1 is there in C also. 2 is in B. 2 is there in C also. 3 is in B. 3 is in there in C also, which means that every element of B is also in C. Therefore, B is a subset of C also. So, we constructed an example satisfying these two conditions. Now, we have to check whether A is a subset of B. In order for A to be a subset of B, every element of A must be in C also. But, see, here we have the element of A is nothing but 1, isn't it? But in this set, there is no element which is 1. Of course, we have singleton 1 as an element. But in A, 1 is the element and we don't have 1 in this set. Singleton 1 is another element. It is not 1. So, we have 1 is one element of A, but 1 does not element of C. Here, we don't have any 1. Of course, we have singleton 1. Don't confuse 1 and singleton 1. 1 is an element in the set A. Here we have singleton 1 is an element, but 1 is not an element in the set C. Hence, we can say that A is not a subset of C. Very important example. Please note it down and understand it properly. If you have any doubt, contact me. So, this is example number 11 of your textbook. So now we are going to find the subset of real numbers. We know that the real numbers include all the numbers in the entire number line, isn't it? Let we have R as the real numbers. Let it be there. We know that the set of all natural numbers include 1, 2, 3, etc. Isn't it? Let it be there. Now we know that the set of all integers include it begins from minus infinity and we have minus 3 etc. minus 3, minus 2, minus 1, 0, 1, 2, 3 etc. Isn't it? Now we have the set of all rational numbers include all the set of all x such that x should be of the form p by q, where q must not be equal to 0 and p and q element of z. So, this is the set of all rationals. So, we have 3 sets here, isn't it? See, each and every element of n is also in z because 1 is in z, 2 is in z, 3 is in z and so on. So, we have n will be a subset of the set of all integers. Now, observe that all the elements in the set of all integers also in the rational set of all rational, because we can denote minus 3 as minus 3 by 1, which is of the form p by q and q not equal to 0, pq element of z. Similarly, we can denote each and every number. 0 can be notated as 0 by 1, which also satisfies all the conditions to be a rational. 0 is of the form p by q, q. Denominator not is equal to 0. P, Q belongs to Z. 0 and 1 belongs to Z. Similarly, we can notate each and every integer which belongs to Z in the form P by Q. So we have Z is a subset of Q. Therefore, we have N is a subset of Z. Z is a subset of Q. Similarly, we can say that N is a subset of Q also. Let it be there. So we have N is a subset of Z. Z is a subset of Q. Now, Q contains all the numbers of the form P by Q. Clearly, Q will be a subset of R. So we have natural numbers subset of integers, integers subset of rationals, a rational subset of real numbers. Also note that let T is equal to set of all X such that X element of R and X does not element of Q. What is that set? Those numbers which element of the set of all real numbers, whereas it does not elements of the it does not belongs to the set of all rational numbers. Such numbers are called irrational numbers. So we used the letter T to denote the set of all irrational. So we have root 2, root 5, pi, etc. in the set C. T. Clearly we know that T is a subset of R because basically each and every element of T is an element of the set R. Also note that those elements are not the elements in the set Q. Then clearly we can have Q is not a subset of T and T is not a subset of Q also. So remember these two results also. So we have this result from this discussion. N is a subset of Z, Z is a subset of Q and Q is a subset of R. Now the set of all irrational. T is a subset of the set of all real numbers and rationals is not a subset of real irrationals and irrationals is not a subset of rationals. Now we shall consider a set. Let A be the set. Let A be the set of all X such that A less than X less than B where A comma B element of R. Let this be a set A, which means that X must be one among the real number in between A and B, isn't it? And A and B are any two real numbers. We shall plot this on a number line. Suppose that this is our entire number line and let it be A and B. So the set A means the set of all numbers in between A and B. That is, it contains all the elements or all the numbers in between A and B and it does not contain A and B because it is a strict inequality. Therefore, we can notate the same thing as open interval AB. Read as open interval AB. So, open interval AB means the set of all X such that A less than X less than B, and that can be notated in the number line as the line segment starting at A and ending at B, and it does not include A and B. In order to notate that, we give a bubble at the ends. So that is what we mean by saying open interval AB. Similarly, we can construct various type of open intervals. Open interval 1, 2 means set of all X such that 1 less than X less than 2 X element of R. So the open interval 1, 2 means set of all real numbers X such that it is in the number line and in between the numbers 1 and 2. Similarly, we can construct lot and lot of open intervals like this. Similarly, we can name closed interval AB as set of all X such that A less than or equal to X less than or equal to B and X element of R. Here we have X element of R. So the only difference between an open interval and a closed interval is that we have strict inequality here, whereas we have a loose end inequality or less than or equal to used here. So in order to show the closed interval, we use darkened bubble in the real number line. So we have in the number line, we have the closed interval AB is nothing but all the real numbers in between A and B including A and B itself. So this is the closed interval AB. Similarly, we can construct very large amount of closed intervals. Let be 2, 3. Closed interval 2, 3 is nothing but set of all x such that 2 less than or equal to x less than or equal to 3 and x element of R, isn't it? Now, we can make semi-closed intervals or closed at the left and open at the right. See, closed interval A comma open B. So this is closed in the left and open in the right. This is nothing but the set of all x such that A less than or equal to, see, closed in the left, A less than or equal to x less than, open in the right. So we use strict inequality there, B and x element of R, which means that it includes the set of all real numbers in between A and B, including A and excluding B. So we can denote it as darkened bubble at the end A and open bubble at the end B. So this is the notation for closed interval A and closed A and open B in the number line. Similarly, we can notate open A and closed B as set of all x such that A less than, see here it is open, A less than x less than or equal to B and x is an element of the set of all real numbers. So this is the way of representing various types of intervals: open interval AB, closed interval AB, or closed interval A and open B, open A and closed B. So this is the various kinds of intervals. Note that in all these examples, the elements in the set are all elements of the real numbers, or we can say that the interval, it can be either closed interval or open interval or open closed or closed open. Whatever, the interval is a part of the real line, isn't it? Or we can say that every element of the interval, see this is the elements of the interval, right? All the points in between these A and B are the elements of the interval, which is also points in the entire number line. So we can say that closed interval AB is a subset of R, open interval AB is a subset of R, closed A, open B is a subset of R, open A, closed B is also a subset of R. Similarly, we can use the notation open 0 infinity, which means that all the real numbers in between 0 and infinity. Now, we can use the notation minus infinity infinity, which means that all the real numbers in the entire number line, which is same as the set of all real numbers. In such a manner, we can use the notation of intervals in order to notate various types of set, which means that whenever we say that we are considering open interval 2, 3, it is actually a subset of R as well as it is a set such that set of all x such that 2 less than x less than 3 and x element of R. That means open interval 2, 3 is actually a set which contains all the real numbers in between 2 and 3. Now consider the set A is equal to set of all 1 and 2, which means that the set A contains two elements, namely 1 and 2. Okay. Now we are going to find out all the subset of this set. We know that phi is a subset of every set. So we have phi is a subset of A also. Now consider the set singleton 1. See, 1 is an element of the set A. Hence we can say that singleton 1 is also a subset of A. Because in singleton 1 the only element is 1 and that element is also in the set A. So this set will be a subset of A. Now consider the set singleton 2, which means that the set which contains only element is 2 and 2 is there in A. So we can say that singleton 2 is a subset of A. That's it. So we have three subsets of A. Now we know that a set is a subset of itself. Therefore set 1, 2 is a subset of A because A is a subset of A itself. So these are the only possible subsets for the set A. That is, we have listed all the subsets of the set A. Now I am going to form a new set with the elements as this set. That is, let B is the set which contains all these set. That is, B contains phi, B contains singleton 1, B contains singleton 2, B contains set 1, 2. So B is the set which contains all the subset of the set A, right? And such sets are called power set. So power set is the set of all, power set of a set A. Let me name this as power set of A is the set of all subsets of A. So power set means the set of all subsets of a set A, and we denote that set by the notation P of A, which means that P of A is the set of all subsets of the set A. Power set of A, it should be read as power set of A, which means that the set of all subsets of the set A. So we listed out all the sets or the sets which are subsets of the set A, and we formed a set using those sets as the elements of the set, and we named that set as power set of A. And observe that A has 2 elements, whereas power set of A has 4 elements. In general, if A has m elements, then power set of A, P of A, has 2 raised to m elements. Very important result, very important result. Never ever forget this result. So see here, if here we have 2 elements in A, then power set of A has 2 raised to 2 elements, which is 4. So whenever A has m elements, power set of A, that is the set of all subsets of A, has 2 raised to m elements, which means that if A has m elements in it, then the number of subsets of A is nothing but 2 raised to m. That means that if a set A has 10 elements, then the number of subset of the set A is nothing but 2 raised to 10. If a set has 5 elements, then the number of subsets of that set is 2 raised to 5. That in a similar way, whenever a set has m elements, power set of A contains 2 raised to m elements. We can also redefine that as whenever a set has m elements, it must contain 2 raised to m subset. Now we are going to define one of the most important as well as interesting names in this session, that is called universal set. So far we have studied about subset, proper subset, superset, power set, etc. And now we are going to study universal set. Universal set means a set which include all other sets in a particular context. For example, if we are dealing with prime numbers and divisors of some number, etc., then the universal set can be either natural numbers if it include all other sets in that particular context, or it can be the set of all integers if it include all the other set in that particular context. Or similarly, if we are going to study about the number of men or number of women in the world, then the universal set can be the set of all human in the entire world, which means that universal set is a set which include all other set in a particular context. That is a set which include all other sets in a particular context. So it depends on the context. So universal set gets on varying according to the context. Whatever be the context, universal set must have a property, that is it must include or it must contain or it must be a superset of all other sets in that particular context. For example, suppose that our set is a set of all male students in the class 11A, and suppose that we have another set in that context, set of all students in class 12B, etc. Then the universal set can be the set of all students in Giridipam school, which means that the universal set is the set of all students, or the set of all students, the universal set is the entire set which include all the students, all the subset, all the sets in that particular context. So universal set in general notion, a set which include all other sets in a particular context. So that's all for today. I hope you understood the basic concepts and descriptions and definitions we dealt with today. So if you have any doubt regarding this concept, ask me. And coming on to the next session, we will solve the exercise 11.2. So before solving exercise 11.2, just watch this class very well, because we are going to use all the notions, all the definitions, all the properties we discussed in this session in the coming session. Okay, thank you for watching. Stay tuned for the next video. Bye bye.